Hello, my name is Andy Schweitzer, and this is a little video on linear relationships, mathematical relationships. Now, this is something that you will cover extensively in math classes, specifically algebra, linear mathematics. And they will take it to extreme levels and do all sorts of mathematical manipulations. But for the most part, in chemistry and I would say even physics, 90 to 95% of the mathematics are linear. So we're going to take a little bit of time here, and we will also do in class look at some simple relationships, chart them out, and graph them, and look at some of the mathematics of how to solve some of these problems or to find unknowns. The overall goal of any mathematics or science, for that matter, would be to predict a future result using some sort of mathematical relationship. So, for example, let's say you are driving in a car, and let's just say this car you are driving at a rate of speed of 25 miles per 1 hour. Okay? Now, this is what we call a relationship or a ratio or a rate. In this case, it's a rate of speed. So if we were to create a data table like this, and let's just say this is your time, and this is your distance. Okay. And I'm going to graph this thing out here, and I am going to put time on the x-axis, and I'll put distance on the y. So very often I'll ask kids who are having trouble with linear relationships, if you're traveling at 25 miles per hour, how far did you go? And very often the student kind of looks at me with kind of a perplexed look, and they're like, well, what do you mean? Like, well, if you're going 25 miles an hour, how far did you go? And the most common answer would be 25 miles. And I'm like, well, no. And the answer is really, you didn't go anywhere. This is not, this is a rate of speed. It's a relationship between distance traveled per time. But it means nothing, it is if you haven't given a time or a distance for that matter. This thing will relate time traveled to distance or distance traveled to time. It's a relationship. It doesn't mean anything. I can travel, across my room at 25 miles per hour. I can throw a baseball at, 25 miles per hour. How far did the baseball go? Well, it just depends how long it was in the air. So this is a relationship, and it means nothing unless it is placed in context. So let's say you're traveling for 1 hour. 1 hour means you have traveled 25 miles. And if you're traveling for 2 hours, you would have gone 50 miles. And then 25 miles, 50 miles. 3 hours, you would have traveled 75 miles. 4 hours, you would have traveled 100 miles. Okay. Now, in this case, let's go, and this is not going to be a real accurate data table, much less graph. 1, 2, 3, 4, and let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these are all 10 miles per hour increments, time-wise in hours. So 10, 20, 30, 40, 50, 60, 70, 80, let's say, and this is 100. All right. And you should note that, you probably realize this is going to be a straight line. 1 hour would give me 25 miles, and then 2 hours would give me 50 miles, right there. And then 3 hours would give me 75 miles, and then 4 hours would give me 100 miles. And I'll just try and make my line as straight as I possibly can, because it would turn out that way if I were to really measuring carefully. Now, in this case, if I were to travel, let's say, and I'm just gonna connect some of these lines up and make myself a nice straight line as much as I can with this particular computer drawing program. All right, so let's just say that I do a different relationship. All right, let's do 50 miles per hour. Okay, not 50 miles per hour, miles per 1 hour. Okay, data table. It's okay. Well, time, distance, and 1, 2, 3, 4 would be 50, 100, 150, and 200. This is very, I would consider this mathematics and graphing very elementary, something you would do in grade school. But in reality, it really mimics a lot of what we do in just standard chemistry as far as relationships are concerned. Now, in this case here, okay, so at 1 hour I would have traveled 50 miles. At 2 hours I would have traveled 100. And at this point I could graph this out here. I don't have graphing space for it, but it will essentially follow a straight line, and at this point it would continue on. Now, for both of these graphs, I can extrapolate or interpolate my lines. I can go beyond the lines or in between the lines to say, well, if I was traveling for 2.5 hours, how long would I have gone? I would just go up and over. If my graph was accurate enough, I could easily do this. Or I could say, well, I didn't take measurements beyond 4 hours, but what if I were to be driving for or moving for 8 hours? Okay, I could extend the line and then again do up and over. The slope of this line represents the speed, distance divided by time, the slope. So either way, these particular graphs lines could be represented mathematically by the equation y equals mx plus b. Now that's okay. I mean, that's very useful. But we're not going to, in this case, look at this particular graph. We're going to use a simple ratio or proportion. And for any linear relationship, and this could be, related to many different situations. I'm using distance over time. It could be spending money at the mall. If you can spend $50 an hour. I mean, if you were there for 10 hours, how much money would you have spent? Okay, it's really anything that is following a straight line or linear relationship. Okay. Now, any linear relationship can be mathematically related to the equation of x1 over y1 equals x2 over y2. Okay. Now, you will see in chemistry, you will see this relationship throughout the year. You'll see things that work like this. And this particular relationship, if you know something is linear, you can use this to solve it for whatever you want. Here's how we do it with this particular equation. So if I would say, okay, x is going to equal let's say the distance. And let's say y equals and I could have used, flipped them around, it does not matter. And I have this as x, this is y, but that doesn't really make a difference in this case. Y would be the time. Okay. And since the distance traveled, and I could use 25 over an hour, I could use 50 over 2 hours. Any relationship point along this slope is going to be the same relationship mathematically. So we're going to go, let's just say 25 over 1 equals, all right, and then I have time, x2 over y2. This would be your distance, this would be your time, and again, all I need to do is plug in a certain time or plug in a certain distance, and I'd find the correlating relationship here. Essentially, it's like coming up and coming over. The slope is fine, but if you give me a time, I can come up and come over to get the correlating data point. So if we're traveling for 10 hours, okay, you'd put in 10 right here, and you'd solve, cross, multiply, and divide is one easy way of doing it. 10 times 250 divided by 1 would be, well, the same thing, 250. Okay, so in that case, the distance would equal 250 miles. Okay, so in this case, this is a simple mathematical relationship. Okay, and it may seem so simple, but in chemistry, we use proportions all the time, and they're simple proportions. when you take these proportions and you weave them into other concepts, sometimes they can become a little more complicated. Okay. Now, this is what's called a linear proportion. We also have something called a reciprocal relationship, where as one thing gets bigger, the other one gets smaller, and that also occurs in chemistry. But at this point, we're just going to look at the linear proportions. Okay. Again, if I were to do some more examples of a linear proportion, I would use x1 over y1 equals x2 over y2. Now, a chemistry example I could use for this might be, let's just say I'm building a water molecule. H2 plus O2 yields H2O. And when I balance this thing, I require 2 right here to balance all oxygens. So 4 hydrogens, 2 oxygens, I need 2 of these. So these things are for building water molecules. I literally would take 2 hydrogens, 1 oxygen, and make 2 water molecules. Again, I would take 2 hydrogen molecules, 1 oxygen, and as I disassemble them and reassemble them here, it would produce, we got 1 of those guys, there we go, and a big one, here we go. And this is before picture, this is after picture. So 2 of these and 1 of these yields 2 of these guys. So this right here is the ratio which they combine and produce. This is the rate which I use, rate used, and this is the rate produced. Okay. So again, you could say, well, let's say for example, and this is a simple relationship, that if I were to consume, let's say X equals the hydrogen, okay, H2s, and let's just say that Y equals the O2, right? And in this case, making out my little relationship, I would say, well, if 2 H2s are consumed, I also consume 1 oxygen. All right, so if I consume, let's just say, 500 H2s, cross, multiply, and divide, my unknown value here, which I was calling Y, Y2 for exact, cross, multiply, would be Y equaling 250. And this might be easy to see that for every 2 of these, I need 1 of those. So if I have 500 of these, I need 250 of these. Pretty straightforward. Okay, this is called a linear relationship, and we use this a lot in chemistry. We take this method and we plug it into some that in our school we commonly refer to as factor label. Now, factor label is just another way of doing a linear ratio. Okay, and after kids use it a while, it's just another way of doing it. Okay, so let's just say, let's go back to the 50 miles per hour. Okay, now this is a relationship. I often refer to this as a flipper. It flips hours to distance or distance to time. So let's say if we were traveling for 3 hours. Now, right away, you say, okay, well, I know the answer is 150. Okay, I understand that. But as things get more complicated, you will want to be able to work with the ratios or work with the factor label, because it won't be as intuitively easy then. And it always causes problems when kids just ignore the process, and then in the end, it gets more complicated, they're stuck. So follow along with the process. Okay. Now, if I were to use this thing using, well, there's only one way to really solve it, reduces ratios. But there are 2 ways we look at these ratios. One is just a simple ratio. X1 over Y1 equals X2 over Y2. And some students will use this method entirely. All right, so 50 is, you have to designate this as my distance. This is going to be my time. So 50 over 1 hour equals, okay, distance I'm looking for, okay, no, they give me time, so 3 hours, and looking for distance, question mark, so cross multiply divide, and the distance equals 150 miles. Okay? Again, not entirely difficult, but that's how we would do it with a ratio. Now, if you were to use factor label, looks pretty sloppy, factor label, all right, and I will see on AP exams, this is the method by which they will explain and show many of the problems. They'll use factor label. And someone else might call it unit analysis. So we have 3 hours, and I would like to convert these 3 hours into a distance. In that case, I need a conversion factor or a ratio, and I sometimes also call this the dot line method, because if you don't know what to do, put dot line. This unit is going to, it's really over 1, so this will cancel right here, and I also, mathematically you should know this should cancel, but very often I'll say, what do you want to get rid of and where do you want to go to? I want to get rid of hours, I'm going to go to, in this case, miles. This is my rate, which is provided in the problem. They're traveling at 25 miles per hour. And in this case, 150 miles is traveled in 1 hour. This is an equivalency. It's a ratio. I'm not changing anything here, the distance, into a miles. It's a relationship, but it's not really changing anything. 3 hours times 50 divided by 1 equals 350 miles. Sorry, it would be 150 miles. Now, for this, the reason why this is nice is because if your units cancel and you're using appropriate, meaning accurate relationships, then technically it should work out that the answer is correct. Okay? We call this factor label. You wouldn't, for example, put this down, 3 hours, okay, dot line, get rid of hours and go to miles. Okay, and in this case, let's just say it's 1 over 50. Okay, this is not a correct relationship for 50 miles per hour. It's 1 hour, 1 mile, and 50 hours. So even though your units cancel, the relationship is inaccurate. Pretty common mistake to get that upside down. Okay. 3 divided by 50 would be a relatively small number. So very often you can think to yourself, okay, I'm traveling 50 miles an hour for 3 hours. I should have a number that's relatively large. 3 divided by 50 is less than 1. So when you make this mistake, it tends to really throw your answer off. And if you're thinking about it and not just following the math, you can often sniff out that mistake. Okay. Brief example into factor label. This will be covered in depth in class and for the rest of the semester.